So thank you for the invitation to speak here. It's wonderful to be part of such a great conference. Today I'd like to tell you about a project I've been working on together with Andy Strominger and the three of his graduate students here, Delilah Gates, Dan Kapitz, and Lily Yichen-Shi, who are here in the audience today. The paper's hopefully going to come out this month, and I'd appreciate to hear some feedback from you. So I don't need to convince anybody here that this is really a thrilling time to study black holes. LIGO's unprecedented historic discovery has ushered in a new era of data collection, and black hole physics is now an experimental science, which is very exciting. And in particular, there's a very exciting experiment that everybody here knows about, which is the Event Horizon Telescope that promises to soon deliver the first up-close pictures of two real black holes in our sky, namely the one at the center of our galaxy, Sagittarius A star, and the other one at the center of M87. So this is very exciting experimentally, but also for theorists, because it poses a pressing challenge to us. In particular, there's an obvious question that we should ask, which is what will the images look like? And it turns out that it's really surprisingly difficult to predict. So naively, you might say, oh, what's so difficult? We know the Kerr geometry. So this is the metric which describes astrophysically realistic black holes. In principle, we think, OK, we know about the space-time geometry of real black holes in the sky. It fits in a line. So what's the problem? Well, the Kerr family is parametrized by the mass m and angular momentum j equals to am of the black hole. And it seems simple, but it's actually deceptive. So for one, even though you can write the metric in a single line, and I think it's always good to start a talk on black holes by showing the metric, it turns out to have very surprisingly complicated properties. In particular, if you consider the propagation of light in this background, which is going to be the subject of this talk, there's a very rich and intricate structure to the geodesics. Another reason why this is not a simple problem is because even though we know the black hole's space-time geometry, it's not alone. It's typically surrounded by an accretion disk. There's also a plasma magnetosphere, which obeys some nonlinear equations in electrodynamics. And there may also be a corona, jets, and possibly many other ingredients. And each of these ingredients obeys messy physics, which makes the problem interesting, but also difficult to study. Now, the traditional approach is to run computer simulations. And these detailed simulations can be time-consuming and costly, and they typically have very many parameters, and you have to scan through a wide swath of parameter space. Now, there's a particular corner, though, of parameter space, which is going to be the subject of this talk, and that's the regime of high-spin black holes, in which simulations can be incomplete or altogether fail in certain cases, as I'll explain later. Now, what do I mean by high-spin black holes? Well, it turns out that a Kerr black hole cannot exceed a certain bound on its angular momentum. In particular, the spin cannot exceed the mass squared. If you exceeded that, then the event horizon would disappear. You'd have a naked singularity and violate cosmic censorship, which we think is something that cannot happen. But if you don't buy that, there's other more subtle arguments that indicate that this bound cannot be violated. Now, a maximally rotating black hole is one which saturates this bound, and so we call it extremal. In the extremal regime, there are many surprising special things that happen. In particular, the Hawking temperature of the black hole vanishes, and the region near the event horizon develops local scale invariance, or conformal symmetry. Now, this is the same kind of conformal symmetry which arises in many other situations in physics, and I think this highlights the unity of nature. And in particular, I think it's important to point out that this observation suggests that physics near rapidly spinning black holes should be constrained by conformal symmetry in much the same way as many near-critical condensed matter systems are governed by conformal field theories. And if we use this insight, we can greatly reduce the number of parameters that are needed to describe the problem and sometimes altogether eliminate them. So in this talk, I want to present to you a prediction that we're making for the polarization that will be received from M87. And this prediction is based on conformal symmetry, which we're using as a guide to help us analytically compute the polarization profile of near-horizon emissions from a high-spin black hole. So this result should be directly relevant to ongoing observations of the Event Horizon Telescope of the black hole at the center of M87. And to be clear, our prediction relies on only three assumptions. So the first one is that the black hole is rapidly spinning. It's in this high-spin regime. And I put a check mark there because I think we have some high degree of confidence that the spin is near extremal. The second assumption is that the Event Horizon Telescope can actually observe these near-horizon emissions, and I'll have much more to say about it. And I optimistically put a check mark there as well because I believe in the EHT team, and I hope that they're going to be able to detect these emissions. So really, it comes down to this final third assumption, which we're making really using the symmetry. And that assumption is the statement that we think the polarization profile of the source should be invariant under the enhanced isometries of the near-horizon geometry. So this might be a lot to take in, but I'll unpack this statement. So after all these words, let me actually outline the calculation that we're doing specifically. So we're going to use the geometric optics approximation to describe the radiation coming from the near-horizon region. And in this approximation, photons are modeled by light rays which propagate along null geodesics. Now, these geodesics will propagate in the Kerr spacetime. I wrote the metric earlier. And they're characterized by three conserved quantities, EL and Q, which correspond to the energy angular momentum about the axis of symmetry of the black hole, and the Carter constant of the particle. Now, for null geodesics, the energy turns out to scale out, but is replaced by a new conserved quantity, which arises because of the special algebraic properties of the Kerr black hole. And that quantity is known as the Penrose-Walker constant, typically denoted kappa. And it can be used to parallel transport the polarization vector of the light ray along the geodesic. So therefore, our computation will split into two steps. First, we have to specify the properties of the radiation of the source, and then we must solve the geodesic equation to determine the resulting signal that would be measured by a distant observer. So these are the two steps. Now, in principle, we can do this analytically, and I could show you all the steps, but it's really quite involved. I don't have enough time, but I just want to give you a taste of what's involved. So the first idea is that we should describe radiation in geometric optics, as I mentioned. And in this approximation, a thin beam of particles is modeled by a narrow bundle of rays. And together, these rays will form a geodesic congruence. Now, geodesic congruences are always described by a tangent vector field. And in the case of massless particles, photons will have a null geodesic congruence. And therefore, the tangent vector field is null. Now, what this means is that only its direction matters. And in principle, the norm is not fixed. But we can fix it by requiring it to be precisely the physical momentum p of the photons flowing down the beam. And additionally, everywhere inside the beam, we can define a polarization vector field, which tells us what the polarization of the photon passing through that point is. So the picture that we have is that we have a beam of light, and there are two vector fields defined within this beam, which is a null congruence. And they satisfy the equations that I wrote down in the corner. The first two are just the statement that the photons obey the geodesic equation. And the next three are the statement that the polarization is perpendicular to the photon's direction of travel and is parallel transported along the geodesic. Okay, so the first step is to fix the source polarization. And the way we're going to do that is using the symmetry. So let's talk about them. The Kerr black hole, as everybody knows, is stationary and axisymmetric. So mathematically, that means that it has two isometries, symmetries of the spacetime, which are generated by the Killing vectors d by dt and d by d phi. Now, general relativity predicts that the near-horizon region of a high-spin black hole develops two additional symmetries, namely dilation symmetry and special conformal symmetry. Now, at this point, I'm not going to explain it much more than that, but I'll have some slides at the end to explain in more detail what this means. But the takeaway here is that there are 4 Killing vector fields in total. This is a prediction from general relativity. Now, it is natural to expect that a spacetime imparts its symmetries to the physics that it drives. So for instance, we know from simulations and theoretical expectations that accretion disks should settle down to a stationary and axisymmetric state, at least if they're slowly accreting. And the reason for that is that accretion onto a black hole is driven by gravity, and so the symmetries tend to be imparted to the physics that's driven by gravity. Okay, so we're therefore going to assume that the source polarization is invariant under the local symmetries of the source in the near horizon. That is to say that the polarization vector field in the beams, which is parallel transported along the light rays, also commutes with the 4 Killing vector fields which generate the symmetries of that near horizon region. So that's our one symmetry-based assumption. Now, to be clear, we're not making a claim as to what the underlying physical mechanism that produces the radiation is. In some sense, that's orthogonal to our approach. We're trying to get away from the details and just focus on the symmetries. And the beauty of the symmetries is that they're sort of insensitive to the details. You can get them wrong or not be exact about them and still get the answer right. Now, of course, this polarization vector has to be parallel transported along outgoing geodesics. And so it turns out that if you impose all these conditions, you get a highly over-constrained problem. But surprisingly, there's a solution which nonetheless exists, and moreover, it is unique. So there's a unique signal that you could get from this near-horizon region that would respect all of its symmetries. And that's the one that I'm presenting now. Okay, so one last slide about the calculation to explain in pictures what's going on. So this might seem like a lot, but let me unpack it for you briefly. The idea is that at the source, we have photons that come out with some momentum p mu, and we choose an associated polarization which respects the symmetries. Now, because we're modeling the light using geodesics, that means we can describe it by the conserved quantities along the geodesics, which I mentioned. And since it's a null geodesic, there's only two relevant parameters that I call lambda and q here, which are the energy rescaled angular momentum and Carter constant of the particle. Now, as I mentioned, there's an additional conserved quantity, the Penrose-Walker constant kappa, which depends on the polarization and keeps track of it. So now we have a geodesic which shoots out from the near horizon region, and everywhere along its trajectory, it obeys the geodesic equation for the photon and the parallel transport equation for the polarization vector field. Now, supposing that this geodesic reaches a distant observer, say the Event Horizon Telescope here on Earth, it turns out that these conserved quantities, which are the same, obviously, at the observer as they were at the source because they're conserved along the geodesic, these conserved quantities, lambda and q, are impact parameters, which tell you at what angle the geodesic impinges upon the observer screen. So if you have an observer that sits at an angle theta observer relative to the axis of symmetry of the black hole, you'd expect a photon with impact parameters lambda and q to hit the observer screen with the Cartesian coordinates alpha and beta. The details of these formulas don't really matter, but I just want to show you that it's completely explicit. And in particular, you can also extract from kappa the transverse electric field to the traveling wave, and that is the polarization vector field that you would see on the screen. Okay, so there are more formulas that we could describe, but that's really all you need to know. And so now I'm going to skip to the results. What are the polarimetric images? What does it look like? So the first thing to say is that a backlit black hole absorbs all the incident light up to some critical impact parameter and will therefore cast a shadow upon the observer screen. So this is a fact that probably all of you are familiar with. And the shape of the silhouette depends on the polar angle theta at which the distant observer rests. Now, our finding is that in this analysis, all the near horizon emissions turn out to be confined to be within the shadow, which is actually good news because that means the backlighting won't swamp them out. So I'm going to show you pictures that we get from this calculation in the following three cases. First, the so-called face-on observer that sits on the rotation axis and looks at the black hole down the pole. Second, the edge-on observer, which sits in the equatorial plane and looks at the black hole from the side. And finally, the intermediate case of theta about 15 degrees, which is thought to be of relevance to M87 because we're looking at it almost down the barrel. So let's dive in. This is the face-on image. So what's represented here? Let me say a few words. First, at the center, there's a red circle, which is roughly where the black hole actually is. Of course, this statement is not so meaningful in curved spacetime, but it's the apparent location of the event horizon where you would see the black hole if gravity didn't bend light. It's not a special surface here, though. The special surface is this shadow, which is a few Schwarzschild radii larger than the black hole itself. The units here are units of m, so the black hole at extremality has a radius of r equals m. And so what you would see looking from above is this swirling pattern, which we call a whorl, in reference to the swirling pattern that you have on top of your head. Okay, so if we put this against a pretty background, it looks something like this. It's axisymmetric, which you would expect because you're right on the axis and you're not breaking any of the axis symmetry. And this is the first slide I flashed at the beginning of the talk. Okay, so let's talk about the equatorial plane, for instance. It's a different situation. And there, the shadow is actually quite different. So the black hole here would be at the origin of the axis. And the shadow actually develops a vertical edge on the side of the black hole that's rotating towards you. And there's a lot that could be said about this. It has a really interesting structure. But for now, I'm just going to focus on the polarization. And so what happens if you look at the black hole edge on, under our assumption, is that you'll get a double whorl. And the reason for that is that there's light from on top of the black hole at the North Pole that's coming up and bending towards you. But you also see a whorl at the bottom, which is coming from the South Pole, light that's going downwards and is deflected by gravity back towards you. And this is reflection symmetric, as you would expect in this situation, because you're not breaking the reflection symmetry of the problem. So if you put it against a dark background and you connect the little polarization vectors, you get these nice streamlines. Okay, so what about the intermediate case? If we're looking at M87 down the barrel, so an angle of 15 degrees, we would get something like this. It's closer to the face-on case. There's a lot to be said about what's going on around the edges of the shadow. There's a lot of structure there, but I also think the light should be quite dim around the corners. And if we do the same thing where we connect the polarization vector field to produce streamlines, we would get something like this. So again, it looks like a whorl, but you're looking at someone's head from the side slightly. Okay, so that's a prediction for astrophysics that we've made using the conformal symmetry, but I made a bunch of statements in my talk which I didn't really explain or substantiate, and obviously in the 5 minutes I have left, I can't rigorously motivate everything I've said, but I want to give you a flavor of the ideas that are involved in this kind of approach. So to explain a little bit more what's going on in this near horizon region, let me pose a small problem to you. So this is a figure that I pulled out from a paper by Bardeen, Press, and Tucholsky from '72 when they first started to investigate properties of the Kerr metric. And what it shows is the radius in Bohr-Lindquist coordinates of various special radii in the Kerr geometry, and there's only two that I want you to focus on. One is R+, the lowermost curve, which is the location of the event horizon. And you can see that when A is 0, so you have a Schwarzschild non-rotating black hole, the radius is at 2m. And when you go to the extremal case, A is equal to m, then the event horizon goes to R equals m. So that's OK. But there's something peculiar that happens, which is that all these other physical scales seem to coalesce on top of the event horizon. And that actually should concern you a little bit. So let's be a little bit more precise. Let's suppose that we have a black hole that's not exactly extremal, but near extremals. It has a small deviation set by a small parameter epsilon. That's what I show in the upper right corner here. And we can ask about what happens to these special radii as you take epsilon to 0 and you make the black hole exactly extremal. So you see that as long as epsilon is not quite 0, they're separated, but as epsilon goes to 0, RMS and R+ will get on top of one another. So RMS here is the marginally stable orbit, or the, I think we now tend to call it the ISCO, for innermost stable circular orbit. And that's the last radius at which a particle in the equatorial plane can remain on a stable circular orbit. Now, it's puzzling that at extremality these two things would come together, because it would suggest that a time-like massive particle on a time-like geodesic would actually be bound to a null trajectory that lies on a null hypersurface, which is what the event horizon is. So there's an obvious puzzle here. Now you might say this is a coordinate singularity, there's a problem with the Bohr-Lindquist coordinates, but it's not, because if you were to go to ingoing coordinates, say, which are smooth across the horizon, this fact would still be true, that these radii would be the same. Now, of course, massive particles don't follow null trajectories, and one way you can see this is that the proper distance measured in the Kerr metric between these two radii is actually diverging as the black hole goes to extremality. So there's something very funny that's happening here, which is that from the perspective of a far distant observer, you have these different scales which seem to be combined, but actually they become infinitely far apart from one another. So what's the resolution? And actually in that original paper, Bardeen and friends had the right idea. And the resolution is that the curvature of space-time, obviously space-time gets bent. And the picture that you should have in mind, this is a cartoon, but there's a way to make it precise, is that there's this throat that develops. And indeed, from the perspective of someone far away, these radii appear to be on top of one another. But actually, if you were near the horizon, they would not be. And moreover, there would be a divergent amount of space-time created right near the horizon. So this cylinder here would have infinite proper volume in the extremal limit. So this is a problem if you're trying to do numerical simulations, because there's a separation of scales. So in order to resolve this, you'd need to have a large grid that incorporates both the black hole and the distant observer that can accommodate both. But your grid would also have to have increasingly fine resolution to see this near horizon region. But in physics, whenever you have a large separation of scales, you can always do a small parameter expansion in the ratio of these scales. And essentially, you can do the same thing here, and the small parameter is epsilon, which controls the deviation from extremality, or equivalently, the depth of the throat. So Bardeen and Horowitz, Gary Horowitz, who's going to be speaking soon, actually used this fact to expand the metric in epsilon, and they found that to leading order, the geometry in this throat is actually described by a different metric, which I've indicated here on this slide. And I only have a few points to make about it. I can't explain all of them in detail, but I want to get them across. The first one is the near extremality. The near horizon geometry develops this infinitely deep throat, which has an emergent conformal symmetry. And in fact, there are 4 isometries generated by the Killing vector fields, which I wrote here. And moreover, this geometry decouples from the far region. So it's described by the so-called neck metric. Neck stands for near horizon extreme Kerr. It's a solution to the vacuum Einstein equations in its own right. And I want to emphasize that it's on equal footing with the Kerr metric. In other words, away from extremality, there's one metric that describes the entire spacetime, but at extremality, you just need 2 different metrics to resolve the near horizon and the far region. And you can get one from the other, you can go back and forth, and there's no one that's more fundamental than the other. Now, the key fact is that the time translation symmetry, d by dt, is enhanced here to an SL2R global conformal symmetry, which also includes the dilations of the throat generated by H0 and some special conformal transformation. The axisymmetry of the Kerr black hole is preserved, and so the spacetime has an overall SL2R times U1 isometry group. And moreover, you can do an asymptotic symmetry group analysis in general relativity, and you'll find that it's extended to an infinite dimensional symmetry. So I can't explain really right now why that is, but I can give you a flavor of what's going on. So the one thing I want to point out is that if you look at fixed polar angle theta, the neck metric, which is indicated above, is actually identical to a warped version of ADS3, the 3-dimensional anti-de Sitter space, which you should think of as a gravitating box. And the gravitating box here is this throat, which you cut off from the rest of the spacetime. And as in ADS3, the global conformal SL2R symmetry extends to an infinite dimensional local conformal symmetry. And this observation lies at the root of the Kerr CFT correspondence, which is an analog in the black hole context of the ADS CFT correspondence that we've been talking about, and which underpins the holographic principle and various related approaches to quantum gravity. So the one thing I want to say is that in the astrophysical context, this symmetry relates the throats of black holes with different small temperatures, which in this case is said by epsilon, and that allows us to do calculations precisely at extremality, where they're mathematically simpler, and then extend the results to near horizon, to near extremal black holes. So the last thing I want to say is that in the last few years, these symmetries have rendered feasible a large number of analytical computations of astrophysically relevant processes in NEC that could not otherwise have been performed, sometimes not even numerically. And for instance, Shahar Hardar is here, and together with Andy and Achilleas, they computed gravitational wave emissions from in-spirals, and there are other papers on the topic. And the takeaway point is that emergent conformal symmetries near critical points play a profound role in modern condensed matter and particle physics, and also astrophysics. Okay, so to conclude, I just want to say thank you, and also good luck to the Event Horizon telescope team, and I really hope to get Polarization Whorls from M87. Thank you.
All right, do we have any questions for Alex?
The reason that you're focusing on M87 is because we're sure it's spinning. And but if Sagittarius star turns out to be spinning, that will also have this?
Yeah, so if Sagittarius A star were rapidly spinning, then the same reasoning would apply, but there would actually be even better. So we've written a series of papers in the last year which were going after various signatures of this conformal symmetry. And one of them, for instance, I think it was also a very promising signal, but you would only see it if you were near the equatorial plane. And so unfortunately, that doesn't apply to M87. So there are different things that you can assume that you want. So ideally, you'd have a rapidly spinning black hole that you're looking at in the edge-on case in the equatorial plane, and then there would be even more things to say. M87 is not in the equatorial, we're not in the equatorial plane of M87, but we can still get this polarization pattern. Sagittarius A star, we are in the equatorial plane of, but unfortunately, I think the best guess is that it's not in this high spin regime. I think the best guess is 60% of extremality. It depends on who you ask, I think.
Okay, we got one question right here first, and then Shiraz.
Okay. Suppose I try to do the same calculation for a Schwarzschild black hole, a non-extremal Schwarzschild black hole. Is it right that there would be no polarization and geodesic pattern that is fully spherically symmetric?
I haven't done the calculation, but I think the answer is that there wouldn't be one. Yeah.
There wouldn't be. Just it's
Yeah,
impossible
'cause
to find a
there's
spherically symmetric.
There's nothing you can see on the screen that would completely respect all the symmetries. Yeah.
This would break the symmetry of rotation.
Right. So in other words, if you look
Right.
at
But in the case of Schwarzschild, there would be no polarization pattern that maintains spherical symmetry.
yeah, what would you draw on this picture that would be as
Yeah, it's just that there's no spherically symmetric vector field on the sphere.
I think that's right. And actually, but this raises an important point, which is that, you know, Schwarzschild doesn't have this infinitely deep throat, so you also wouldn't necessarily expect there to be a lot of matter radiating. But here, there's an infinite volume, an infinite proper volume of spacetime, and there can be a lot of matter in there. If there's matter that's been accreting for a long time, there will be an infinite amount of matter in the limit where the black hole is really extremal.
Yeah, I have two questions. One, in some sense, might be related with what he was just saying. So first, did I understand correctly that in order to apply the conformal symmetry, you are really assuming extremal, or are you a little bit away from extremal? So, because I didn't see any spin value in your talk.
Yeah,
so is it 1 or is it 0.999,
So
whatever?
That's a very good question, and there was no way to do it justice in the short amount of time I had. So this is what I was trying to allude to here. The idea is that these are calculations which should hold exactly when the black hole is precisely extremal, but it's not like if you introduce a small deviation from extremality, everything just suddenly breaks apart. It's exactly the same as what happens in condensed matter systems. So I didn't go into this, but all I want to say is that typically when you approach a critical point, the key thing I want you to look at is here, you find that various physical quantities will go like T minus Tc, which is how far away you are from the critical temperature, to some power, which is the critical exponent. And the exact same story applies here. So if you go slightly away from the critical point, things will slowly start to break. And depending on what signal you look at, you know, the symmetry will get broken at different rates. Now,
Because my second question, I don't want to take a lot of time, because my second question was, if you want to measure this, maybe you don't want to compare to the Schwarzschild case, but you could have a spin of 0.6, for example, 0.8 or 0.9. How different will be the pattern, the polarization? Because in that case, I guess you also have this effect, no? It's rotating, but just with a smaller spin. So are you going to see a big difference?
So I think for this calculation to work, you have to be in a fairly high spin regime, so 0.9. Mathematically, what's going on is that we're doing a perturbation expansion in the parameter epsilon, and to be precise about when it breaks down, we would have to compute the next order correction.
No, but I'm not talking about your calculation.
Oh.
I'm saying people may have computed in other ways, what maybe with ray tracing, what is, you know, the signal that you would see with when the spin is not close to extremal. How does it compare your calculation?
Good. So one thing we've looked at concretely is a black hole at the Thorne limit. So there's some argument due to Thorne that black holes should accrete matter and gain an angular momentum until they eventually stabilize at around 99.7% of extremality. That was an argument that Thorne came up with. And that amount of spin is in this regime. And there was an earlier paper that we wrote in the fall last year where we studied the propagation of light in that regime, and we found really surprising behavior, which we described as critical behavior. And I think we've talked to some people who do ray tracing. Of course, in principle, you should be able to see numerically, but I think it would be very, very hard because of many complicated physical things that happen.
All right, let's thank Alex again and move on to our next speaker.